So good evening to one and all who will be watching this session. So till now no one has joined this session. So anyway, but I will just get started with the session. So I will be recording this session and uploading this. So so let me just begin with a quick introduction about myself. So my name is Parth Joshi. So I am a PhD student in the Department of Mechanical Engineering at IIT Bombay. And I am also a recipient of the Prime Minister's Research Fellowship for doctoral research. And as a part of this fellowship, I got this opportunity through NPTEL to interact with all of you and to conduct these weekly interactive sessions. So I hope the previous interaction sessions so far were helpful. So till now we have been looking at system modeling for different kinds of systems like mechanical, electrical, hydraulic, pneumatic, etc. So in the last week, we saw some fundamental building blocks or some small subsystem models for these different types of systems. And in this week's content, we will be going through some problems where we have a combination of, let us say, electrical and mechanical, which is known as electromechanical systems, and also hydraulic and mechanical systems, also which is called as hydromechanical systems. And then we will also be looking at the some of the concepts related to linearization of system equations. So in general, most of the governing system equations, or basically the governing differential equations, we usually get them to be non-linear. So how do we linearize them so that uh, it, like about a certain operating point by which we can use this simplified and linearized differential equation uh, to simplify our further analysis and use them in transfer function models for further control system development. So if we approximate these system equations about a certain operating point, which we know that there will be small perturbations with respect to that operating point, then we can use such linearized models for small deviations from those operating point, which describe the behavior approximately about that operating point. And in addition to that, so there is another content which is related to system modeling of robots, which also has been covered in this week. But for today's session, I will not be covering problems related to that. In today's session, I will be mostly covering problems related to the simple system modeling for uh, basically how to linearize the differential equations, and I'll be covering an example on that, and also I'll be covering some problems on which are similar to the assignment problems for this week. So, so I hope all of you are finding the content related to these sessions useful. So please let me know your feedback, and and if there are any further questions related to whatever the content covered for this week, and also content related to the problem solving session. So please post your questions on the discussion forum for this course. So let us now begin with the problems for this week. So, so the first concept that was covered in this week was basically linearity and non-linearity of systems. So one common problem that all of us must have studied since from high school science, like physics problems. So which is basically the problem of a simple pendulum. So, so when we say simple pendulum, we assume that, so if we draw a diagram for that. So let me first share my screen. So let us first start with the problem of a simple pendulum. So for a simple pendulum, we uh, let us say construct a simplified diagram for this thing, like which consists of a rigid rod connected to a pendulum bob, which has a certain mass m, and the I lost the screen sharing. So let me share my screen again. So let us um, first try to derive the equations of motion for this simple pendulum in the most generalized form. So, so let us say if we draw the free body diagram of this simple pendulum, so the forces that will be acting on this pendulum will be basically the weight of the pendulum and the tension acting in the rod or string by which the pendulum is suspended. So let us say that the pendulum makes an angle theta with respect to the vertical. So now we apply Newton's second law to this system. So when we apply the Newton's second law, so what we say is that uh, summation of net forces is basically, now see, so this is the usual Newton's second law. Now we could also apply the further version of this similar Newton's second law. So where we consider the moment. So the net moment acting about certain point is basically rate of change of angular momentum, or so in rate of change of angular momentum. So in our case, since we are assuming this to be a point mass, this simplifies to the moment of inertia of this system with respect to some point and the theta double dot. So we assume that this is the rod that we are considering, that is massless. So then our only point mass that we are left with is the pendulum bob. So then the differential equation that we get uh, now will be, so if we consider the net moment about, let us say, the point O about which, let us say, it is suspended, so then the net moment of the forces about this point O will be basically the moment due to this force mg and the moment due to this force t. Now since the line of action of this force t passes through this point of suspension O, so the moment of this force t about this point O will be 0, and we will be only left with the moment due to this force mg, and this line of action of this force mg is at a distance of L sine theta with respect to the vertical. So then the moment of the force mg will be basically to L sine theta. So it will be basically minus I theta double dot. So because since our theta is in clockwise direction and this moment is in anti-clockwise direction, so the signs of these both these quantities will be opposite. Now what will be the moment of inertia I about this point O? It will be basically this point mass m into L square to theta double dot. So now if we further simplify this differential equation, we get that minus g by L sine theta is equal to theta double dot, or theta double dot plus g by L sine theta is equal to 0. So now this is the general form of the differential equation for this. Now generally what we do is that we assume that sine theta is nearly equal to theta for small angles. Now this small angle approximation is in fact a linearization of this differential equation, because once we assume this to be a small angle, so I'll just rewrite the differential equation now. So theta double dot plus g by L sine theta is equal to 0, and if we assume that then this differential equation will transform into theta double dot plus g by L theta is equal to 0. So then this is a linear second order ordinary differential equation. So now this approximation is valid only for small angles. So when we linearize a differential equation about a certain operating point, so that operating point is generally a certain equilibrium condition for this system. So now the equilibrium condition for a simple pendulum is either theta equal to 0, or it can be theta equal to 180 degrees. So in both of these uh, conditions, the pendulum is in equilibrium. So the tension force in the string or whatever rod, that is exactly balancing the weight of the pendulum, and the uh, pendulum is in equilibrium or stationary. But if we observe that if we slightly displace this pendulum towards one side, so in case of the theta equal to 0 degrees, the pendulum will start oscillating. So then in that case, basically there is a restoring force which tries to bring the pendulum towards the equilibrium position. So therefore that is called a stable equilibrium position. Whereas in case of the theta equal to 180 degrees, even with the slightest displacement from this position, there will be a further force acting on this pendulum which will take it away from this position, and it will never return to this theta equal to 180 degree position. uh, like it will never exactly remain stationary again. So then that is why it is called as a unstable equilibrium position. So let us consider our case of theta equal to 0 degrees as our stable equilibrium position. So that is an operating point for our system. So now if we consider, if we write down the the series sine theta as a series or a power series, so what we get is sine theta is theta minus theta raised to 3 by 3 factorial plus theta raised to 5 by 5 factorial, and so on. So this is the usual series that we get for sine theta. Now if we neglect the higher order terms, what we get is our originally what we consider as our small angle approximation, as sine theta is nearly equal to theta. So this is how we actually get that approximation, and then this differential equation now will become linear. So that is an example of how we linearize our differential equation about our operating point. So this is one simple example which I wanted to cover, because this is something that we have been familiar with since a long time. So hopefully that will help you to understand this uh, better. So let us now move on to our next problem. So in this problem we have been given a rack and pinion mechanism, and we have been asked to derive the relationship between the input torque and the output velocity for the rack and pinion arrangement. And it has been given that R is the damping coefficient between the rack and guide. Hello, hi, I see that uh, Mr. Venkata Subhash, you have joined. So, hi, welcome. So, since no one had actually joined this session, so I had just started with uh, one simple problem, and I had started recording this session. So, so what I had covered is basically an example of a simple pendulum, and I had explained the derivation of how do we derive the differential equation for this simple pendulum mechanism, and then derive basically the equation in its most general form. So which is basically theta double dot plus g by L sine theta. And then how do we basically come to the usual what we call as our small angle approximation for the simple pendulum. So that we may not have realized earlier, but that is in fact how we linearize that differential equation about a certain operating point. So in this case, our operating point is one of the equilibrium positions of the simple pendulum. So in case of this, we have two equilibrium positions, so which is 0 degrees and 180 degrees. So one of them is a stable equilibrium position and another is unstable. So we consider the case of 0 degrees as a stable equilibrium position, and if we now write down the sine theta as in the form of a series, we get the sine theta as it is shown over here. So now if we neglect the higher order terms, we in fact get the usually what we call as the small angle approximation of sine theta is nearly equal to theta, by which we now have linearized our differential equation about theta equal to 0 degrees. So that is an example how we can linearize simple systems. So
Sir, I
I'm
have a small doubt, sir.
sorry.
I have a small doubt, sir. Can I ask?
Yes, yes.
Uh, in the second step, you wrote sin theta is equal to theta, no, sir.
Which one?
In the second step, sir,
Second
you
step
have
in the
written the arrow mark. Yes, sir.
which one? You mean this part here? That arrow mark.
Yes, sir. Sin theta is equal to theta.
No, so that is just to explain that, if we consider that usually what we call as that small angle approximation, we get that, that kind of a differential equation. But how do we come to that equation of sine theta equal to theta that I was explaining after that? So we first, like, we write down the usual power series that we get for sine theta, and then if we neglect the higher order terms, then that in fact is exactly the same as, so this is in fact like a Taylor series for sine theta. So
Yes, sir. Yes, sir. It is Taylor series. But
yeah,
can you exactly say it is equal to theta or it is similar to theta, sir?
no, for small angles we can neglect the higher order terms in that. So then only the first term will be left. So that becomes our approximation for small angles. So then that is basically a linearization of the differential equation. So we might not have realized that this fact, like, what this is, what we do usually, but in the context of linearization and non linearization of non-linear differential equations. So the um, the original differential equation for this problem is theta double dot plus g by L sine theta. So this one. So that is the original differential equation for this problem. Now, so this is actually non-linear. So in order to linearize that, we would have used that kind of an approximation. So, okay, is that okay?
Yes, sir. But in the second step, it is equal to theta, and the last step, it is similar to theta, sir. That is only I have the small doubt, sir.
No,
That's
no.
why I asked.
So this is also same as nearly equal to, like, this is basically what I had. This is just to show that uh, it's one and the same thing that I have done. Basically, it's not different from that, whatever I have done in that arrow mark thing. This is just to show how the equation will become linearized when we actually incorporate this approximation. Is that okay?
Okay, sir. Okay, sir. Thank you, sir.
Yeah, thank you. Okay, fine. So since like none of you had joined earlier, so I had already started. So let us now move on to our next problem. Now before we begin with the next problem, so I hope like you know me by because I think so you might have attended the earlier problem solving session. So have is there anyone of you who are attending this session for the first time? Okay, fine, fine. So yeah, so for your just information, so my name is Parth Joshi. I'll just quickly introduce myself. So I'm basically a PhD student in IIT Bombay from the Department of Mechanical Engineering, and so I am conducting these weekly interaction sessions for this course, and this is the fourth week. And so till now we have discussed problems related to the particular course content for this week, and in this week we will be basically discussing the course content related to the as I just covered the concept of linearization, and then electromechanical and hydromechanical systems. I am in design engineering, so I basically did my masters in design engineering. Uh, so MTech. So I did my MTech from IIT Bombay, and now I am doing my PhD again at IIT Bombay. And before joining PhD, I was working in industry for a few years. So that is the introduction about me. And I got this opportunity through NPTEL and through the Prime Minister's Research Fellowship. I got this opportunity to conduct these interactive sessions with you. So whatever sessions that have happened so far, I think you will get the recordings on the NPTEL course website. So yeah, I'll provide you my email ID. Uh, so you can also go through the previous weeks, whatever previous 3 weeks online interaction sessions, and you can watch the video recordings of those. And so let me know if you have any questions later on in our next future sessions. So so your name actually shows something like vampire roaming. So what is actually your name? Okay, your name is Omkar. Okay, fine. So are you a BTech or MTech or like what's are you a student or are you working in industry? So you have already done your masters in design engineering. Okay, great. From BITS Pilani. Okay, fine. So even I did my undergrad from BITS Pilani. Okay. And are you working in industry somewhere? You are working. Okay. So you are from mechanical engineering background itself? Oh, last 22 years. Okay, great. Okay, so then you are much older than me. Okay, great. So great to have you, Mr. Omkar. And what about you? Okay, so you did your master's in 2022. Okay. So from which institute did you do your master's? So you just mentioned about BITS Pilani, right? Sorry. Yeah. And yeah, so thanks. So great to have you on board. So, and regarding Mr. Venkat Subhash, so uh, are you currently studying or are you working somewhere? So you are working. Okay. So have you completed your masters or fine. So Mr. Venkat Subhash, so have you completed your masters? Okay, so you are a faculty in mechanical engineering. So okay, fine. So are you doing your PhD or have you completed your PhD? So you are pursuing PhD. Okay, great. Fine. So both of you, thank you for joining. So I hope this session will be useful for you. So today I'll be covering some problems related to the content for this week. So there were like 4 or 5 topics in that. So first, which we just covered, linearity, non-linearity, and then modeling of electromechanical and hydromechanical systems. So we'll be covering some examples related to that, and hopefully that those will be helping you to understand the course content on this week. And there is also another uh, lecture on the system modeling for robots. So that is a separate and big topic. So I have not included those problems related to that in for today's session. So I'll be focusing mainly on the electromechanical and hydromechanical system modeling. So fine. So any questions or comments related to the content for this week? So I just wanted to know from both of you. So how do you find the content for this week? So is it easy? Okay, so you completed your MTech in machine design in the year 2019. Okay, fine, thanks. So both of you are basically from mechanical engineering background, as I understand. So yeah, fine. So how do you find the course content for this week? So is it I mean, do you find it easy to understand or do you find it difficult? And so regarding the I mean the so you are not clear about bond graphs. Okay, fine. Okay. So what exactly is the aspect that you were not clear? So I mean, is the concept itself or like anything specific related to bond graphs that you were not clear about? So you have not applied it in life. Okay, fine. That's okay. Okay, fine. So we had actually covered the concepts related to the bond graphs. So what I would suggest is that you can actually watch the video recording for our previous, um, the session previous to this. So it was, I think, in week two. So the recording for week two. So I have explained the concepts related to the bond graphs. So what I would suggest that you could actually try to watch that and let me know. Yeah, so I'll provide you my email ID. So and then we can discuss separately uh, what exactly that you were not able to understand. So I would suggest that you please go through that video and So in the initial part of the video, I have tried to explain some of the basic concepts on that, and then some problems have been covered. So hopefully that should help you clear some of your doubts, and if any, and if there are some more doubts left, that we can actually discuss separately over email. So I'll just provide my email in the chat. So I have posted my email ID in the chat. So I hope you have received it. So I think we might cover Simulink also slightly to some extent later on. Right now we are just covering the basic theory related to system modeling. And I think towards the later part of the course, I think we will be covering something on some examples on using MATLAB as well as Simulink. So I can also separately cover Simulink if you are interested, and I mean, I can also try to cover some examples if at all that you are interested, even if that is not part of the course. Sure. Yeah, welcome. So fine. Anything else? Anyone had anything else to say? Fine. So then we can actually start with this problem, and so so this problem is related to use basically modeling mechanical systems. So here we have a rack and pinion mechanism. So there is some, let us say, some electric motor which is running the pinion, and it is providing some input torque T in to the pinion, and then this pinion is in contact with a rack mechanism which is installed over a certain guideway, and there is some friction which is between the guideways, and so basically R is the damping coefficient, or basically in some sense it's the coefficient of viscous damping or viscous friction between the rack and guide. So now we have to derive the relationship between the input torque and the output velocity for the rack and pinion arrangement. So now how do we start with this problem? So so we first um, consider each component separately. So we first consider the pinion and consider what is the net torque acting on the uh, you know um, torque acting on the pinion, and then we apply Newton's second law to it. So we assume that, let us say, if this is the pinion, so it's given that there is some input torque T in. So we also assume that there is some output torque, net output torque that the pinion is able to provide. So we can write down the differential equation. So for this, so basically the direction of this output torque will be actually reverse, because so since the pinion is pushing the rack forward in this direction, so then it's actually providing a force in this direction. So as a reaction of this, so the reaction force which is acting on the pinion will be in this direction, which will cause a reverse torque which is in a clockwise direction with respect to the axis of the pinion. So we can write down the equation of motion for this pinion. So the net torque basically that is acting on this pinion will be basically the moment of inertia of this pinion and the moment of inertia of this pinion about its axis and the rate of change of angular velocity. Now, so let us say this force acting on the rack because of this pinion. So let us call this as F. So the we can write down this force in terms of the torque basically applied by the pinion onto this rack. Uh, so this force into the radius of this pinion will be equal to the net output torque that is provided acting at the pinion. So let us call that force as F. So now the if we draw the free body diagram of the rack, so let me draw this. So then there will be a friction force which is, so since the velocity is in this direction, so the friction force will be opposite to the velocity, which is basically r into the velocity v, and there is a force F which is acting because of the pinion. So there will be this force acting on the pinion, and let us say if the mass of this rack is uh, small m, so then we apply Newton's second law to this rack, and what we get is basically mass into acceleration of this rack is basically the sum of the net forces acting on this rack, so which is basically the force F, which is T out by small r minus r into v. So this is the equation of motion for this particular rack. So now using this equation, we can derive this expression for the torque T out. So now we can rearrange this equation. So we get this equation for T out. So now we substitute this equation of T out in this differential equation for the pinion. So we write that T in minus so we get this differential equation now for the pinion. Now we know that the velocity which is imparted to the rack will be r into omega. Basically, omega is the angular velocity of the pinion multiplied by its radius. So that will be the tangential velocity at the point of contact between the rack and pinion. So using this, so we get that d omega by dt will be 1 by r into dv by dt if we differentiate this relationship. And if we substitute this into here, then we get that. So now if we now rearrange this equation, we will get that. So this is the differential equation that we get uh, for. So now, so basically we get this differential equation in terms of the input torque and the velocity of the rack that we were find out. So basically this is the differential equation between the input, which is the input torque, and the output is basically the velocity of the rack. So this is the governing differential equation that we get. So so are you able to follow? Okay. So were you able to follow? Okay, fine. So let us now move on to a next question, which is basically related to the deriving the differential equation for a DC motor. So it has been given that uh, there is a DC servo motor. We have to derive the differential equation between relating the input voltage and the output angular velocity. We have to assume that the motor is armature controlled and the equivalent circuit of the motor has an armature with just resistance. So we have to neglect its inductance. So any idea how do we approach this problem? What about you, Mr. Venkat? Okay, fine. So let me just explain from the basics. Uh, so so when we model like basically derive the differential equation for a electric motor, what we do is basically we try to represent the electric motor as a equivalent circuit. So so the electric motor has mainly two components. So it has a rotor and a stator. So for a DC motor, we have so the we have armature. So the inner part of that is generally called as armature. So we have armature windings on top of the rotor, and then we have different poles. So either we can use permanent magnets to provide the magnetic field, or we can use an electromagnet. So we can either use different kinds of windings on these poles by which we can create a magnetic field. So the basic principle on which the electric motor works. So are you aware of that basic principle? What is the basic principle? Okay, so what is the basic principle on which this electric motor works? Or let us say if a simple DC motor, what it works on, what concept? So uh, the DC motor basically works on this principle that a current carrying conductor, when it is placed in a magnetic field, yes, conversion of electrical into mechanical, yes, Faraday's law, yes, yeah, exactly, right, exactly, right. So Lorentz law, yes, 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 exactly. So that's the same thing. So the when we place a current carrying conductor in magnetic field, and then the interaction between the uh, conductor and the magnetic field, so that so there will the current carrying conductor will generate its own magnetic field, and when it is placed inside a magnetic field, so then the two magnetic fields will interact and then give rise to this whatever what you call as Lorentz force. Yes. So let us say if we draw a let us say some coil. Um, so let us say if there is a coil which is I'm showing this coil as a square shape which is a planar kind of coil, and let us say the current is flowing in these directions which I have indicated using the arrows. And let us say there is a magnetic field. So this let us say if this coil is placed between the north south poles of a permanent magnet. So let us say there are two the poles of the permanent magnet. So the magnetic field we can draw it like this way. So we can indicate a magnetic field by this arrow. So now we can predict the direction of the Lorentz force from this. So so if we consider this part of the you know the current carrying conductor, so the direction of current over here is like this, and the magnetic field is like this. So now using the law that the force acting on the current carrying conductor is basically integration of I into dl cross b. So basically the cross product between the direction of the current and the vector of magnetic field, we will get the direction of the force. So it will be, so if this is the direction of the current and this is the direction of the magnetic field, the direction of the force will be perpendicular to both of them. So it will be like this. Whereas if we consider the left hand side part, so here the current is acting in this way and the magnetic field is acting in this way. So now the force will act downwards. So the directions of these forces are basically equal and like the directions are opposite and the magnitude of forces is equal. So this gives rise to a couple, or basically there is a torque or generated or moment generated about the axis of this coil. So then there is a net torque or net moment that is generated because of this interaction between the magnetic field and the current carrying coil. So likewise, if we have multiple such coils wounded on top of let us say some stator, um, so that is called as armature. So there will be some multiple number of such coils, um, and which will be placed inside this magnetic field. So the outer part of this, which is called as stator, so that has some windings, which is called as, either we can call them as like field windings. So because of the interaction between them, we basically get the torque generation, or basically that is how the motor will start spinning. Yeah, rotor and stator, yes. Now we basically try to represent this into kind of like an equivalent circuit. So these coils, each one of them, they have, so d omega by dt is kt upon jra to be okay. Okay, so you're already aware of the uh, okay. So I didn't get your question, sir. So for a Python or MATLAB code, so actually didn't understand your question. Convert the differential equation. Okay. Okay, so we'll come to that. So we'll just quickly write down what will be the equivalent circuit for this. So each of these armature and field windings, they will have some certain resistance as well as inductance. So if we draw an equivalent circuit, so let us say we represent this part of the motor, like or basically the armature. So we indicate LA and RA, basically those are the inductance and resistance of the armature windings. And so this is the uh, rotor of the electric motor. So let us say the omega is in this direction and the torque generated is this way. And let us say the load, there is some load on the which the motor is driving. So let us this say that this load has a certain polar moment of inertia. So we can call it as I or J or whatever. So let me call it as capital I. So this is the armature windings part, and there will be similar equivalent circuit for the field windings. So here for the armature, let us say VA is the input voltage applied to the armature windings, and similarly for the field windings, let us write down the, so let us say VF is the input voltage applied to the field windings, and RF and LF are basically the resistance and inductance of the field windings. So let us say the armature current, we indicate it in this direction, and let us say the field current or in this windings is IF. So this is the usual equivalent circuit for electric motor. So we have been given in this case that we can inductance, the inductance is negligible. So we will incorporate that approximation later. So first we will just derive our original differential equation. And it has also been given that the motor is armature controlled. So when we say that the motor is armature controlled, that means that the magnetic field created by the field windings is constant. So basically, which means that this field current is constant. And the basically the speed of the motor is basically we can control it by adjusting the armature input voltage. So you have raised a hand. Yes, you have some question. Venkat, you had some question. How can you calculate the time constant? So we can calculate the time constant by by basically the uh, determining the step response of this system. Uh, so by measuring the damping, so for that we'll have to do like go further from this problem. So it's slightly different from this problem that we are looking at, but we'll come to it later.
Okay, sir. Thank you.
It's a servo, so it will be a control loop. Yes. So right now we are just putting the simple basic model of the electric motor. I am not looking at the control loop part exactly right now. So we are not concerned about how the the exact control logic for how we change vary the armature voltage, etc. So we are just looking at the basic model for the electric motor. So basically, if we write down the Kirchhoff's voltage law for this both these armature and field windings, so what we get is that this voltage VA is basically equal to the sum of the voltage drop across each of these components. So across the motor there will be a back EMF that is induced because of the uh, current carrying conductor basically placed in so the conductor which is placed in magnetic field, so because of the changes in flux um, passing through the coils, so there will be a induced EMF, back EMF, which will oppose the change that is causing it. So since our field current is constant, so this term will actually be zero. And since so therefore we are not worried about basically the field coil. So because we'll just assume that the field created by those things, the magnetic field is constant because the field current is constant. So we can say that the back EMF VB, so that is generally we can write it as some constant, let us say K2 into B omega, and the torque, it is let us say some K1 into. So we basically can write that torque is K1 into B omega, and the back EMF is given by K2 into B omega. Now since it's an armature uh, controlled motor, so then B is also constant, so we can write it as something as K3 into omega, and the torque as again as some K4 into omega. So now I made a mistake over here, so it should be, it's basically proportional to the armature current. So since B is constant, so we can write it as like VB is the back EMF as K3 into omega, and the torque, let us say we write it as K4 into the armature current. And so basically let us write down the equation for net torque. So the net torque acting on the load. So let us say there is some bearing friction and some torque loss because of the viscous damping. So we, let us say we call that RB is the coefficient of viscous damping, and omega is the angular velocity of the motor. So then we can write it as, so so let us now come to our Kirchhoff's voltage law for the armature windings. So we can substitute this value of VB into this, and so the back EMF will be actually K3 into omega. So okay, yeah, I think that is correct. So using basically that torque is K4 into IA, so we get basically K4 into IA minus RB omega is I d omega by dt. So using this we get an equation for IA in terms of omega. So we get IA is basically RB omega plus I d omega by dt into 1 upon K4. And we can substitute this into the differential equation over here. So we can substitute in this differential equation for this IA. So we get that VA is, so then since this we have been given to be that this is 0, so this is how we get the governing differential equation in terms of the input voltage to the armature windings, and the output basically output is basically the speed. So we get a first order differential equation in terms of the angular velocity of the electric motor. So we can also further simplify and rearrange the terms over there. What do you exactly mean that without explicit application of KVL? I actually didn't get what exactly you meant. Yeah, I understand Kirchhoff's voltage law, but what do you mean that without explicit application of that? So I didn't actually get what you meant by that. So this is like the basic thing, like the Kirchhoff's voltage law is like the basic thing that you can apply for this, and then using the like basic proportionality relations for like the torque is proportional to the armature current and the back EMF is proportional to the angular velocity of the electric motor. So you have basically the torque constant and the speed constant or back EMF constant. So you can add, like, instead of K4 you could actually write it as KT into IA, and this thing, so instead of K3 we can write it as KE into omega. So I think you have done that. So and so it's essentially, I think, the same thing that we would be doing. Yes. So any questions? So if not, so let us move on to our next problem. So this problem is related to the flow rate through an orifice. So we know that this the equation for the flow rate uh, through the orifice in terms of the pressure difference between the two ends of the orifice, that is proportional to the square root of the pressure difference. So the relation between the flow rate and the pressure difference is non-linear. But if we want to linearize this equation, so let us say for an incompressible fluid, time constant for the previous question. Okay, okay, fine. So that, so shall we? I think that will actually come into the content for the next week. So uh, the part of actually the step response and and basically the that time constant part. So that's actually going to be covered in the next week session. So I actually had not especially prepared for that part. So is it okay if we calculate, like, if I show that calculation in the next week session? Okay. So you have already calculated. Okay. So what formula did you use exactly? Can you just share what exactly have you done? So if possible, if you can share your screen or share a picture of what you have done. So can you just unmute and tell what exactly have you done?
So good evening, sir.
Yes.
Sir, actually, I have calculated by comparing with A1 dx by dt formula is there, no, sir?
I actually could not hear you clearly. Sorry.
No, I'm audible, sir.
Yes, yes.
I compared it with A1 dx by dt plus A naught x is equal to B naught y, sir.
I'm still not able to hear you clearly. Um,
Okay, I will type in the chat box, sir.
yeah, okay, fine.
Okay.
So I had actually not exactly prepared for that part of calculation of time constant in this week. So because it's already going to be covered in this week, so we would be covering that in the next week definitely. So in the meanwhile, if you can share what exactly you have done, so compared it with the formula A1 dx by dt plus uh, Okay. Okay. So you compared the differential equation with that form. Okay, fine. So you mean basically if we try to solve this differential equation, basically the solution for omega in terms of the uh, so I actually just lost my screen sharing. So let me just share my screen again. Yeah, I think your approach is correct that you are trying to basically looking at the usual form of like the first order differential equation and then trying to compare the coefficients and get the time constant. So I think that approach is okay. Is that what you are trying to do basically? So like the first order differential equation like of this form, right? So we are getting like so if we divide by this uh, I into RA by K4 on both sides, so we will get that differential equation or like of the first order kind of form. So I do not exactly remember the formula as such, but we can basically solve this differential equation and the uh, basically we have to multiply. How do we solve this differential equation is by multiplying the integrating factor, right? So so how do we find out the integrating factor? So like if we have a differential equation of the form, so let us say if we have a so dy by dx plus some q of x is equal to some p of x. So how do we find out the integrating factor? So we find So we multiply this by the integrating factor, right? So and then yeah, so e raised to integral p dx, p of x dx, and then multiplied the integrating factor on both the sides, and the solution is basically this is what we generally get the solution, right? Yes, exactly. So we the left hand side will be the product rule, basically the derivative of y and e raised to integral p of x dx. Exactly. So like this is how we can solve this differential equation. I think we will, if we solve this differential equation using the same approach, we will get to the solution of that similar form. So the does that answer your question, Mr. Venkat? No, no. Actually, the thing is that we can, instead of so here we can simplify this differential equation and like put it into that same kind of form. So so this is, let us say we call this as some C1 and this is some C2. So we have this C1 d omega by dt plus some C2 omega is VA. So we can divide by C1 on both the sides. So we can have this C2 by C1. So it's now in this similar kind of form. So our integrating factor would be what? So it will be e to the power integral C2 by C1. So it's not x, so it's with respect to t. So here it will be dt. So we will get the solution of this form. So basically omega will be So this constant K is the constant of integration. So this VA by C1 is again a constant. So this term will actually get cancelled. So we will be left with this kind of a term. So the e to the power minus C2 by C1 t. So that will be basically the thing that will have the time constant part. So it actually depends upon this ratio of C2 by C1. So I think whatever you were calling it as A1 by A0 or something like that. So it's actually the same thing, like whatever we are calling as C2 by C1 or whatever. So based on that, we will get the time constants. So does that help? Is that okay? No, no. There is no vibration analysis as such. So this is just the no, this is not related to vibration analysis as such. So this is just uh, so we apply a certain voltage, and then the time constant is like it's like, let us say if we apply a voltage now uh, corresponding to, let us say, a RPM of 2000 or something like that, and then now we measure the time required for the motor to attain that, basically come to that speed. So then the motor will take some time to accelerate because of its own inertia to come to that, basically to reach that speed. Let us say to attain that 2000 RPM, let us say it took 1 second or 2 seconds or whatever. So then the time constant is basically the time required to for the motor to accelerate from zero speed up to something like about 60, it's about something like 63% of the maximum whatever speed that for which we. How can we apply the same in the axial flux motors? I actually am not aware of axial flux motors, sir. So I am not an expert in electric motors. So sorry, I'm not aware about axial flux motors. So Mr. Venkat, are you okay? Are you satisfied with this explanation of like how do we calculate this time constant thing? So the time constant will be proportional to this ratio of C2 by C1. uh, So the time constant as such will be, let us say tau is the time constant, it will be basically C1 by C2 itself. So I think we should move to the next problem. My voice is not clear. Okay. I think maybe there's some internet lag in the internet connection. So there may be some problem in that. Maybe that is why my voice is not clear. Anyway, the session is being recorded, so if you are not able to hear some part of the session, so you can just watch the video recording and that will help you. So I think, yeah, sure. So let us move on to our next problem. So we were discussing about an orifice. So this is the governing differential equation by which we describe the flow rate in terms of the pressure difference. So just one thing which I don't think I'm not sure whether you were able to follow that or not. So basically we got the solution in the previous question as omega is. So here the exponent basically e to the power minus c2 by c1t. So generally the first order differential equations, so they have the time constants. So e to the power minus t by tau. So here tau is basically our time constant. So that's why I wrote that this tau is basically c1 by c2. So that is how we basically get our time constant by comparing that coefficients. And what was c2 and c1? So we have defined our c1 and c2 in this way. So which is given in this slide. Okay, fine. So let us proceed to this problem for the orifice. So this is the equation for the flow rate in terms of the pressure difference. So this is non-linear. And suppose if we want to derive a linearized equation for this flow rate in terms of the pressure difference and the cross-sectional area, then how do we do that? So for that, we we can basically take the partial derivative of q with respect to a. So since the coefficient of discharge is constant, and for an incompressible fluid the density rho would be constant. So since it's an incompressible fluid, so rho is constant. And similarly we take the partial derivative with respect to, let's say, p1 minus p2. Then what we get is cd into a into. So this is the partial derivative that we get with respect to this. So let us call that this, let us say this slope as m1 and this slope as m2. Then for the operating point, which is represented by the pressures P10, P20, and the area of cross section A0, we will get the value of m1. So it will be basically CD into P1 naught minus P2 naught by rho, and m2 will be CD into A naught. Now for the flow rate to be linear with respect to the both the cross-sectional area and the pressure difference. So what we do is basically we can write that delta Q is, so if we write the partial derivative as in this form, so for small finite changes about the operating point, so we can write it approximately like this. And for small finite changes in the pressure difference, so we can, yes, yes, exactly. So that's the exactly the same thing. So if we have to combine them, so then we can just add both of them. So we will get the expression as m1 into delta A. So the combined expression of linearized flow rate with respect to the cross changes in cross-sectional area and pressure difference. So we get this as the final expression in terms of those slopes about the operating point. So, yeah. So let us now move on to our next question. So since we are short of time, so we'll just quickly go over the remaining questions. So there are not many questions left, and most of them are, I think, small now. So yes. So so this question is about potentiometers. So it's about basically what is the input and output about in a potentiometer kind of a device. So what do you think is the answer to this question? Yes, it's D, because both B and C are correct. So potentiometers can have either linear motion and giving out proportional potential difference, or we can have rotary potentiometers where the potential difference is proportional to the rotation. So D is the correct answer, both B and C. So the next question is where we have a coil of wire wrapped around an iron core and the flux equation is given. And let us say if you have 100 turns, what will be the voltage produced at the terminals of the coil? So basically we have to calculate what will be the induced EMF. Yes, yes, exactly. So the variable resistor, what is called as rheostat. So that is an example of where we have linear motion, uh, linear movement proportional to the potential difference. And yes, obviously in the radio you have the transistors, and so there that's an example of the potentiometer where you tune the radio by changing the resistance value. Now the next equation is about this. Next question is about this flux and what is the induced EMF. Uh, so here we can apply what law shall we apply over here in this question? So the induced voltage opposes the change in flux. So and so basically that is the Faraday's law. So the induced voltage will be minus N into d phi by. So if there are n turns of the coils, so the voltage will be proportional into the turns, number of turns, and the rate of change of flux. So it will be basically minus 100 into 0.5 into omega cos omega t. Yes, so it will be minus 50 omega cos omega t. Yes, clear. So shall we move to the next question? So this is basically Faraday's law. Minus is must be basically because it is opposite to the change in flux. So that's why like you can say minus. Yeah. So in this question, it's asked that MCQ. So the MCQ type questions will be there in the assignment. In the exam, you may not have MCQs, so you will probably have more of subjective type questions. The weekly assignments are MCQ type. So yeah, basically, so this in this question, so it is asked that what does the back EMF or the electric motor depend on? Rate of rotation of the armature, the flux linked with the coil, or both or none? Yes, you're correct. So it is basically both A and B. So the it will depend on both rate of rotation as well as the flux. Basically, it will depend on the magnetic field. So the back EMF is uh, proportional to the magnetic field as well as the angular velocity. So the angular velocity that is clear. So the flux will give rise to the magnetic field. So that in this way it is linked the flux linked with the coil. So that is like depending on the magnetic field and the flux will be interdependent. So that's how both A and B will be the answers to this question. Yeah. So this will be our last question for today. An orifice meter with diameter of 10 centimeters. It is inserted in a pipe of 20 centimeter diameter. So let us draw the diagram here. So this is our orifice. So this is 20 centimeter and this diameter, orifice diameter is 10 centimeter. So there are pressure gauges fitted upstream as well as downstream. So let us say this is P1 and P2. So P1 gives a reading of 19.62 Newton per centimeter square and P2 is 9.81 Newton per centimeter square. So the coefficient of discharge is zero point 0.6. So we have to find out what will be the flow rate considering these are the pressure values. So we will apply just this directly this equation of CD into cross sectional area A into root of 2 into P1 minus P2 by rho. So can you please just try calculating what will be the value of the flow rate using this equation? So rho will be 1000 grams per centimeter cube. So since all these units are in terms of centimeters, so let us stick to centimeters here. So the area will be 10.82 lpm. Okay. So let us, I haven't yet calculated yet. So yeah, we'll check what will be the answer. Okay. So I think let us stick to SI units. Uh, so if we, so P1 is 19.62 in Newton per centimeter square. So in terms of Newton per meter square, it will be into 10 to the power 4, and rho will be 10 to the power 3 kg per cubic meter. And area will be 10 into 10 to the power minus 2 squared. Yes. So you wanted to ask something? So I'm getting something like around 0.066 uh, meter cube per second. So which will be 66 into 60 into liter per minute. So I think that's the answer to this question. So these were the problems that I had for this week's content. So I hope these problems have helped you understand some of the concepts. So, so I was not able to cover the problems on the system modeling of robots part. So it's a big topic in itself and it will require substantial amount of time for that. So I will try to upload some problems on that, but I won't be covering those in today's session. Um, yes, yeah, I can share my WhatsApp number. I have posted my WhatsApp number on the chat, so you can contact me on WhatsApp also, no problem. So this was all that I had in terms of the problems for this week. So any questions, comments that you had? So you can contact me uh, like generally after 7 o'clock in the evening. Sure. So we can you can contact me on phone, like we can discuss and talk over call, no problem. So you can message me on WhatsApp and then we can decide mutually what is the time if you have anything to discuss. Is that okay? Yeah, sure, sure. Yeah, thank you. So I think we can close the session for today. Thank you, both of you, for joining. Thanks. So I think we can close the session for today. Thank you. Thank you. Good night. Take care.